Waves in the ocean, light, sound, or even the ripples that you make when you skip a stone on water. We all know what these have in common. They're all types of waves. But did you know that you can classify these waves in different types of families? My name is Farah and this is Gwen. We're both graduate students in the Space Systems Lab at MIT. And today we're going to show you the difference between some of these types of waves by using equipment that we use every day in our labs.
One important thing to note, though, is that although all these types of waves are different, their properties can be explained using the same equations. For example, there's the amplitude, which is how big or loud a wave is, the frequency, the time period, even the energy of a wave. We'll also show you really easy ways to calculate these things.
Now, there are two big families of waves. The first are mechanical waves, such as sound waves or water waves, and these need a medium to travel through. The second type of waves are electromagnetic waves, and these can travel through a vacuum. Examples of those are light waves or radio waves. And the difference between these two types of waves explains why, if you're in space and there's an explosion, you could see the explosion, but you wouldn't actually be able to hear it.
Today we're going to focus on mechanical waves, that is, those waves that need a medium in which to travel. As engineers, we're a little bit more interested in this type of wave because we deal with them every day and they're really easy to see. And within this family of waves, there are three subtypes: longitudinal waves, transverse waves, and surface waves.
This is a transverse wave. As you can see, the direction of the oscillation of the wave, which is up and down, is perpendicular to the direction of motion, which is towards and away from me. Because the wave isn't moving in space, and by that I mean that it is restrained between Gwen and I, it is also a standing or a stationary wave. As Gwen increases the speed at which she moves the rope, the frequency of the wave also increases. Another type of transverse wave would be the waves you see in the ocean. They are oscillating up and down, and yet they are moving towards the beach in a direction perpendicular to their motion.
Now, to better see what's going on, let's keep the image still for a second. So the wave properties of this rope are pretty easy to see in this image. The amplitude is the height of the wave we've formed, and it's this distance here, A for amplitude. The wavelength is the distance between two consecutive peaks, lambda for wavelength. The time period is the time it takes for this wave to go through a complete oscillation. And it's the inverse of frequency, which is how many waves go by per unit of time. The velocity is the number of wavelengths traveled in 1 second. So wavelength over time, if time is seconds in this case. And since time equals 1 over the frequency, v, or the velocity, is also equal to the wavelength times the frequency.
Here is a simple voice recording program which I have on my computer. I use this quite often when I interview scientists about their work, for example. As I talk, the program records my voice and shows the types of waves which I am creating. Sound is also a mechanical wave, but it's a longitudinal wave. That is, the wave which is created by my lungs pushing air out of my mouth oscillates in the same direction as it is going. Sound is essentially little pulses of air which your ear detects and then translates into words or music.
Let's pause the screen again to see what's going on. So again here, you can see the amplitudes of all these little waves created by Farah's voice. The greater the wave is in amplitude, the louder the noise that's going into the microphone. This time the wavelengths are a lot shorter. In fact, you can't even really see them because they're so compressed. And the time scale is a lot smaller. That is, the wave is moving more quickly. The higher the pitch of the sound, the more compressed the wave is on the screen. This means that a higher pitch corresponds to a higher frequency.
The third type of mechanical wave is a surface wave. That's the type of wave you would see if you dropped a rock in a still lake, for example. Unfortunately, those waves are a little harder to reproduce in the classroom. Thankfully, some students at the MIT Media Lab have created a device to help us visualize surface waves. So let's go over to the MIT Media Lab and see Cody, who's a student there. He's going to explain to us exactly how that device works.
Good to see you.
So tell me, what's going on here?
So this is a project, part research, part fun, called Ping Pong++. And basically what it allows us to do is actually see the surface waves that you've been talking about in person. So we have a normal ping pong table, but if we take the ping pong ball and drop it, suddenly we get the visualization of the waves.
Pretty neat.
Now, the mechanism for doing this actually relies on these same surface waves except in a solid. So underneath the ping pong table you have a series of sensors, so wherever there is a point of vibration, it's able to triangulate that back to a singular point. So that's a little bit of how it works.
Want to play?
Let's do it.
The same wave concepts that we talked about earlier can also be seen here. Amplitude is a little bit more difficult to see than it was with the rope or the sound recording program, but it corresponds to the intensity of the light making the ripple. So for instance, you can see that the ripple on the table is a little bit brighter along the top here, while it fades off into darkness at the bottom of that wave. On a 3D surface such as water, the amplitude would be the height of the ripple. So imagine this is the surface of water, and a rock is going into the water. The ripple it would form would be a lot like this. And this is where the rock went in. So you can see that the amplitude is the height of the wave above the water surface. The wavelength is the distance between each ripple. So this distance here, lambda, or the wavelength. Here the time period and frequency are a bit harder to visualize because you're not watching it dynamically, but essentially they're the time period basically between the ripples generated from this locus where that rock went into the water.
Well, we had a lot of fun talking about waves to you today. Let's go through what we talked about. First of all, there's two big families of waves. There's mechanical waves, which need a medium through which to travel, and electromagnetic waves, which can travel through a vacuum. We talked more specifically about mechanical waves because they're much more fun and easier to see, and we told you that there's three subcategories within them. There's transverse waves, whose oscillations are perpendicular to the motion of travel. Then there's longitudinal waves, which have oscillations that are in the same direction of the motion of travel. An example of the transverse waves was the rope that we used, and for the longitudinal waves we showed you a program which recorded my voice. And finally, the third category is surface waves, and we showed you that through the really cool ping pong table down here in the Media Lab. Now, we also mentioned two broader categories of waves. There's standing waves, which aren't traveling or moving anywhere, and we showed you that again through the example of the rope on the table. And there's moving waves, which travel through space and eventually dissipate, and examples of that are sound or the surface waves that you saw on the ping pong table. Well, we showed you all sorts of ways to display waves in order to help us understand the concepts behind them. But did you know that on top of enabling us to talk to each other, a different type of waves, the type that you play with when you're at the beach, can actually be used to generate electricity? If you're interested in the work that MIT has been doing in developing technology to harvest this renewable source of energy, just go to the website shown at the bottom of the screen. Well, that's all for us today. I hope you enjoyed listening to us, and see you next time.